First of all, I need to introduce my esteemed panel. Immediate left is David Sedlak. He is an environmental engineer and currently the Plato Malo, I have a hard time pronouncing it, Zamenhof Professor at the University of California, Berkeley. He's previously the editor-in-chief of the American Chemical Society's ES&T and ES&T Letters, great publications that many of us use. His research interests are chemical contaminants and water resources. A great honor, he was elected a member of the National Academy of Engineering in 2016 for contributions to environmental aqueous chemistry. Not many people get elected to that. He earned his PhD in water chemistry from the University of Wisconsin at Madison in 1992 and his BS in environmental science from Cornell University in 1986. Sitting next to David is Adam Laputz. There's a joke there, and I won't say it. Licensed professional engineer and assistant executive officer with the Central Valley Water Board. Adam is a licensed professional engineer and assistant executive officer with the Central Valley Water Quality Control Board. He has over 2 decades of experience in water quality programs focusing on a whole bunch of the things that the board does: the surface water permitting, irrigated lands, water recycling, waste discharge to land programs, the MPDS point source permitting, TMDL basin plan sections, and very importantly for the discussion today, the Central Valley Salinity Alternatives for Long-Term Sustainability, otherwise known as CV salts. Adam holds a bachelor's and master's degree in chemical engineering from the University of Nevada, Reno. And then at the far end is Dr. Pegu, is a professor in the Department of Civil Engineering, New Mexico State University, and she is the research director of the New Mexico Produced Water Research Consortium. Dr. Yu leads basic and applied research on water quality, water reuse, membrane processes, and renewable energy-powered water treatment and desalination programs. The goal of Dr. Yu's research is to address critical water challenges in arid and semi-arid regions using non-traditional water supplies such as brackish water, produced water, desalination concentrate, industrial, and municipal wastewater. And if anybody has, what is it, $300,000? Let us know, because we're looking for a contract, for money right now to kick off a produced water project. Money's scarce these days like hen's teeth. With that said, a lot of the talk is going to be focused one way or another about salinity in this valley. And it's long been known that we have a salinity problem. And it started coming to the board's attention back certainly in the latter part of the last century, to the point where on January 30th, 2006, there was a joint meeting of the Central Valley Water Board and the State Water Resources Control Board, chaired by Chairwoman Tam Dudek. And focused, of course, on desal in inland areas. And I envy those people on the coast that have the ocean to discharge to. One of the things that we wanted to do was to take our salt water, if you will, to the ocean. And we did a study on taking it, in fact, to the East Bay Municipal Utilities District plant that is there near the Golden Gate Bridge. And it would have gone through their plant and into the, discharged into the San Francisco Bay at that point. When you looked at the costs, transportation costs, O&M costs, on getting that water there, and then of course it had to be treated, there were treatment costs. Because don't forget, this water contains not just the salts that you would say get out of ocean water when you're desaling, but it picks up contaminants such as arsenic, selenium, and a lot of other things that have to be addressed in the treatment process. And we looked at the costs, and it was way too expensive. Certainly the water that would have been made available by the original desal would have been too expensive for ag to use. So what do you do with it? And so then we start looking at inland disposal. And there's a lot of parts in this country and elsewhere in the world that have this problem with inland desal. What do you do with a brine stream? There's been some talk of drying the salt out, stacking it up. But you have to realize a lot of that salt has to be handled as a hazardous waste because of the contaminants that are in it. Costs of that are quite large, and the management of that, and it's going to be blowing from time to time when we have winds, and I can imagine a contaminated salt being blown around the valley. We're not going to be very popular. So the issue is to try to find a way to manage that, and there are some steps being taken in that direction today. Some new technology that's, of course, we know about conventional desal, but there are some new technologies that's being developed and some on the horizon, which is very exciting. And it's that technology, I think, will may provide some of the answers we need for producing materials that are valuable. As was mentioned by Scott, in the last presentation, they're making acids and bases and a lot of other materials. Both selenium and arsenic are not mined in this country, but they're essential to the electronics industry. We buy those in quite large quantities from places like China and Africa. So there's opportunities, and I could go on, but there are opportunities to making some money there, and being able to lower the overall cost of the water that we're providing for use. Also, if we start doing desal using certain strategies within the valley, we can give a priority to disadvantaged communities that don't have water supplies, of producing them with clean water streams. So we can go on and on of the advantages of doing this. The question is, the science isn't quite there where it has to be. In the presentation given by Matthew Harkin, I believe his name is, earlier from Metropolitan, if you happen to notice a very long, about 20, 30 years, just to get to the point where you can turn your plant on, once you go through demonstration and the research that's needed. So that's why it's important to start now, and we're on the way, I hope. So with that said, I'll be quiet and let the speaker speak. And first speaker is Dr. David Sedlak.
Yeah, well.
You can also turn this one on.
Oh.
Yeah, you can use this one too.
Afternoon. This one will be fine. So thanks, Carl, for the introduction. Thanks, Isaiah, for having me here. And thank you all for being here this afternoon. One of the things that Carl didn't mention in his introduction to this session is that some of the work that Thomas Harder and his colleagues have done on the nature of the valley and the fact that it's a closed basin, and all the salt that comes into the valley today, most of it stays behind. And this is an issue that may take 20 or 30 years or longer to resolve, but failing to resolve it means that there won't be agriculture in the valley in 80 or 90 years. And they've done research showing that the status quo won't hold. And so this is what scientists often refer to as a wicked problem, and it's time to start planning for a longer-term solution. This is not something that's going to be solved overnight. So I want to try to tell you a little about the work that we've done with support from the Department of Energy's National Alliance for Water Innovation, or NOWI, to start to try to pick up a little bit on where that CV Salt's initial project that Carl mentioned with the pipeline and discharge to the bay, and try to think about a path forward for us. Some of it was the dissertation research of Zipporah Wagner, who graduated last spring, and some of it is work in progress from my colleague David Zilberman, who's an agricultural economist, and his student Daniel Shariat, who has helped him on that. And that work hasn't been published yet, but I want to tell you a little about it. So let me start by talking about the way in which we've moved from the idea of disposing of salts to managing them. And I want to start way back in the year 1886, when Professor E.M. Hilgard from UC Berkeley, a soil scientist, made a trip to the Punjab in India and saw the way in which irrigated agriculture in an arid climate had led to salinization and waterlogging of soils. And he came back to California and warned Californians that if you're going to insist on irrigating agriculture in California, you're going to have to deal with the salts. And that warning from Hilgard was taken by the government when the California, the federal project was built, because that project was built not only with a means of bringing water and importing it into the valley to enable irrigated agriculture, but also dealing with the salts. And that was the San Luis Drain, which you can see in this map here. But the original idea behind the San Luis Drain was to offer a way for the salts from the valley, from irrigation, to make it to San Francisco Bay by way of the Delta. The federal government reneged on its promise to send that water all the way to the Delta in 1968, and a great idea came along of building a large evaporation pond, which would also serve as a wildlife refuge, called the Kesterson Reservoir. And that project got started, and I remember as an undergraduate in college, the news program showing pictures of ducks born with crooked bills because they were living in the selenium-impacted waters of the Kesterson Reservoir. And so the disaster of Kesterson, this idea that you could just send that salty drainage water to the desert and let it evaporate, became apparent, and the Kesterson Reservoir was closed down. And there was no way really to get that salty water out of the valley. And so a period from 1975 to 2005, which consists of an exciting time for lawyers of having lawsuits, and people trying to develop partial solutions, things like trying to sneak some of that salt into the San Joaquin River during times when it was flowing, doing something called land application, which is essentially salinizing areas selectively with the salts and letting them go downhill, and fallowing land ensued. And that period was kind of depressing to watch. And that's why when CV Salt showed up on the scenes in 2006, a lot of people were quite happy to see that happen, because it was finally the idea that a local solution might be born for this problem of getting salts out of the valley. And that certainly was the great hope. And so this first study that Carl just mentioned here, here's a picture of a pipeline that was proposed in this feasibility study that was run by some consultants that CV Salt's contracted with. We could call it the desalter and pipeline scenario. And just to give you a sense of that project, it proposed 33 desalination plants, with each one about the size of that El Paso plant we heard about in the previous talk. So imagine 33 of those being built, 25 million gallons a day each, a 450-kilometer-long pipeline, which would carry 75 million gallons per day of concentrate from those desalters. This is, I guess, maybe 4 times as long as the Metropolitan pipeline that we heard about this morning. A discharge to San Francisco Bay, which I think anyone who understands the politics and the science of discharge to San Francisco Bay is probably the most fantastical part of this whole scheme, because just discharging a little bit of nitrate or a little bit of selenium, for example, from an oil refinery is difficult enough on its own. And then this issue of cost. And if we think about the cost of the project, it had a CapEx cost or capital cost of over $10 billion, which would make it more expensive than the project we heard about from Metropolitan this morning. That's in 2014 dollars. And a levelized cost of water of about $3,270 an acre feet. So you guys think in terms of acre feet. Remember this morning, we were hearing about $50 an acre foot for managed aquifer recharge. And of this, about 2/3 of the cost was involved in the handling of brine. Remember, we heard half of the cost of the LA Metropolitan project was brine management. This would be about 2/3. So clearly this was a non-starter. But what was really interesting about it to us was that it showed that serious people recognized the existential nature of this problem and were willing to consider ideas that seemed like they were too hard to do. And that, to me, seems like a great opportunity for research and development to take technologies that are not economically feasible and try to make them feasible and try to bring them up to that level of technology relevance. And so one of my jobs in NAWI, the National Alliance for Water Innovation, was I had this great title of lead cartographer, which means that I was in charge of making roadmaps for where we were going with respect to our research. And after helping out with the agricultural water use roadmap, I saw a real opportunity here in the San Joaquin Valley to start thinking about how emerging technologies could be employed to start addressing this issue. So this paper here, or this report, which you can scan the QR code and get the download to it, is a result of a workshop. And Carl was one of the conveners, Isaiah was one of the conveners of that workshop, and a few other people involved in NAWI convened a workshop, and we had a grant to think about an alternative to the idea of the 450-kilometer pipeline. And so our research elements were to have this workshop, and the workshop was in February this came out in February 2025. It took almost a whole year to write this up. An economic analysis, that's why I had an agricultural economist, David Zilberman, as a partner. A series of structured interviews with stakeholders involved in this, so that certainly we weren't going to parachute in from the ivory tower of UC Berkeley and tell people in the valley how to manage their water. We wanted to hear from them what they thought the best way to do this was. And so I wanted to share with you briefly a few key insights that maybe will seed our discussion. One was that we already knew that brackish water desalination for municipal use was half the price of that project that was proposed initially by CV Salt. So the technology's advanced enough in the last 12 or 13 years that we could certainly do brackish water desalination combined with ZLD, or zero liquid discharge, basically turn the brine into solid salt for about half the price of that original 32 desalters. We also learned from growers and other agricultural users that they have a high preference for technologies that are low capex, high opex. That is, they would like to pay lots of money for water technology, but only during drought years. And then they'd like that technology to go away and not to have to pay interest on it in years when they have plenty of water. And so with this in mind, David Zilberman identified this idea that the way in which technology change happens in the water sector, like, for example, in drip irrigation, is by early adopters. And those early adopters are people who have the potential for making high profits and are facing real scarcity and salinity issues. And so think almond growers in parts of the valley on the west side where the water is already becoming salty and they're seeing the end of the line and the prospect of fallowing their land as the people who do this first. And then they build technology knowledge and they transfer this to others in the area. And then finally, one of the things we learned as we engaged stakeholders is that if you're going to solve the salinity issue in the valley, you also have to think about the municipal water supply, or to help communities realize the human right to water. And desalination may play an important role in that by helping small communities treat water that would otherwise be unusable, not only due to salts, but to things like nitrate. And so this is the scheme that Zipporah came up with in her research, the idea that we could create brine recovery and innovation centers, or BRICS, if you want to call them, something that you can remember. And the idea here is that small decentralized desalination plants could provide water for communities that don't have an adequate water supply and for growers, while at the same time addressing some of this brine management issue that we're grappling with, and that the brine would be processed at a centralized brine recovery and innovation center, where we could valorize it, and Pei will tell you a little about the valorization that's happening in El Paso. We could recover water, and we could get those salts in one place and manage them more effectively. And during this process of building this, we learn and drop the price, because as we build more of things, we make them cheaper. And we all know that from rooftop solar, for example, which dropped in cost by 2 orders of magnitude over a 30-year period as people chose to invest more in it. And so just thinking about the discussion that we're going to have today, I wanted to outline some key challenges and research questions that I think would be important for us to address to understand whether this could be a viable solution. One is the issue about the desalination system size. So when you think about it, you can either build permanent facilities like those 25 MGD desalters that were described in that CV Salts plan, or you can build mobile units that could come and go to the places where irrigation is taking place. Of course, the centralized facilities would need some sort of access to aquifer storage, or an ability to put that treated water into a canal, whereas these mobile units could be much more expensive because of all the challenges of mobilizing and demobilizing them. There's this question of brine transport. So once you've desalinated the water, you have to deal with the brine. We've heard about that a few times today. One thing you could do is you could pre-treat it near the desalination site in order to reduce its volume. You could build small pipelines. I was hiking in the Central Coast this Thanksgiving, and I kept running across these small oil wells that were pumping, and they had the oil that they had, and they had pretty small pipelines that went very long distances to centralized places. I think people in the valley know how to move water around. They probably could figure out how to move salts around. And then you have this alternative of possibly using trucks or trains or something to move the salt, but that gets complicated and expensive very quickly. And then finally, there's this question of what to do with the waste salts. So even though valorization is a wonderful thing, there's going to be some solid waste, some salts that are not useful as a product. And there are all kinds of questions like, is there an in-valley disposal solution like deep well injection or a surface landfill where we could put these things? Or do they ultimately get exported by truck or train? And so I just wanted to seed some ideas for discussion and then turn this over to Adam's next. Carl? Yeah. Yeah, that's me.
Adam, you're up.
Do you see yours?
I do, yeah. Okay, let's see here. Okay, good afternoon. Well, it's a tough act to follow. It was a great presentation and a lot of great history there that Dr. Sedlak provided on the valley and how salt management in the valley has progressed over the last 50 years or so. Or I guess the best way of putting it is we've had a problem for a very long time. People have recognized it, and there's not a great solution. I'm going to talk a little bit about our CV Salts program. This program, Carl gave a great discussion on it. It started. It was the beginning of its beginning was a joint board meeting. Very difficult program to get off the ground. And something that Carl was instrumental in pulling together a large group of stakeholders to do this. So I'm going to talk very briefly about the program and some of the things that we've been doing in it. So who is CV Salts? It's really a stakeholder-led program of industry. Agriculture is a large player. We have dairies. We have industries throughout the valley, food processors. We have regulatory bodies. We have the state water board, the regional water board, DWRs there at the table, and many other agencies and entities. And so it's everyone coming to the table, trying to find a solution for this problem that's going to be workable in the long term. And I think that's going to be, that's part of the reason it's taken as long as it has to get our legs under us is because of just the vast number of entities at the table. But I do believe that having that together now and having those entities come together in the way they have, what we do and finally do wind up with, I believe will be the most workable solution and the long-term solution that will get us past the point that we've been for a very long time, and that is trying to find something that works. So I'm just going to briefly, this is a slide, David really covered this very well. Salt salt moves with water. So whenever you move water, you move salt. It's and as we move, a lot of water into the valley from the Delta Water Project down, and we irrigate lands with that water. That water is used by municipalities. Every use of that water, it causes salt to increase in that water or concentrate essentially. And so over time, what we've had is you see our three basins here. The Sacramento River Basin is very well drained. Even though we do a lot of irrigation in that watershed, because of the Sacramento River, because of the amount of rainfall we get up there, we see really, really good drainage up there. We don't see a lot of major salt problems. And then you have the San Joaquin River Basin, poorly drained for the most part. We have the east side, which is east of the San Joaquin River, and the west side of that basin, and the delta, much of the delta's part of the delta's in that basin also. The only real drainage we currently have in that basin is the San Joaquin River. And essentially, we do export quite a bit of salt out the San Joaquin River, but it's not nearly the amount of salt that comes into that basin. So that's problematic, and I think at one point we tried to calculate the amount of salt that comes into these basins in rail cars, and I've heard figures of it could stretch to New York and back or something like that at one point. I couldn't find the exact figure, but it's a lot of salt that doesn't leave the valley. And then you have the Tulare Lake Basin, which is, for all intents and purposes, closed. You do get flow out of that basin very rarely. I think maybe once every time we have really, really major winter events, we'll see flow from that basin into the San Joaquin River Basin. But for the most part, that's a closed basin. So I think the take-home message here is essentially we have no way to drain the salt that's leaving right now. We can't, the places, everywhere you want to have a sustainable water source, you have to have a way to remove the salt. If you continue to concentrate it, you have to find a way to remove it and export it or do something with it. So the salt control program is really a three-phase project. And we're in phase one of that project right now. And right now, we're conducting a large-scale, what we're calling a prioritization and optimization study. The study earlier on that you heard about, where we talked about the brine line and how we might export those salts in a brine line, that was a really what I'd say brute force analysis. It essentially looked at the salt coming into the valley and said, okay, well, every bit of salt coming into the valley has got to be exported. So we got to find a way to do that. And it looked at, that very simple equation. What we're doing with the prioritization and optimization study is taking a much finer look using some of the modeling tools that people have talked about to understand where is salt building up? Where is it going to continue to build up and be a problem? and where is it not going to build up and be a problem, and start to ask the question of, do we have to essentially export every pound of salt that comes in, or do we have to manage the salt in such a way as to ensure that we can continue to sustainably use our water, considering all the different types of uses we have? And so that's part of the goal of that, is to assess the options, what is the current loading, and try to find a long-term solution to salt management. Phase 2 is project development, talking about project design and permitting at that point, and also development of regulatory options for permitting that. And then, oh, something just happened there. Hold on a second. Okay. Then phase 3 would be implementation. So long project, but it's also a project that it didn't happen overnight, and it's not going to be solved overnight. Am I running long, Carl? Are we time okay? Okay. Is my time okay? Okay. So here's the study timeline real briefly. We're right here. We're identifying problem areas. You can see that's the current work we're doing. And we're coming up with what we're calling planning targets. And so the idea there is to determine what amount or what level of salinity in that water for the use of that water is essentially, if we have that use of our water over time, are we going to achieve that target? And if we exceed that target, that's where we're going to see our planning areas. So for example, for certain areas of the valley, we might have current conjunctive use of water where, like the west side, where we're using some surface water supplies, we're using some groundwater supplies. As we get more and more salinity build up and more salts, those waters are going to increase in salinity. And so what we've done is use our modeling tools to determine where the highest problem areas are. And so here's essentially a map, a series of maps where we've done that. And it shouldn't really be surprising to see where the problem areas are. We don't really see much of anything up in the Sacramento Valley region, but as we move south, we start to see more and more problem areas. The interesting thing that did come out of this analysis, and here's some more more maps here, a little bit higher, a better scale. The interesting thing, so you see yellow and orange there, those colors, and purple. So essentially, okay. The yellow and where we're seeing yellow here, we're going to exceed our planning targets in those areas. So salt's building up in those areas. We're not going to be able to deliver water in those areas under the how we manage current water supplies at salinity less than that would be useful at those levels. So we're talking about conductivity greater than 1,000 these would be exceeding conductivity of 1,000. So those are our first steps. We've come up with now some of these problem areas. What we are noticing in this is that areas where we have a high reliance on groundwater for our uses are the areas that are turning up to be the most problematic. I don't think that it should be. It's pretty obvious. If you're using that water, you're bringing it up, you're applying it to your cropland, it's getting back down there, you're going to concentrate. You've got to close the loop there. And so that's what we saw. Many of the areas where we see a large amount of conjunctive use, where we have good, high-quality surface water supplies coming in, we don't see those problems. Okay, this is just another timeline. That's the end of my presentation. I did have one other thing I did want to talk about is we see this, the one thing that, the challenge we see in CV salts, I think, is that I want to add a question to David's questions is, it's one thing to be able to pull the salt out of water. I think we can do that. We've proven we can do that with current technologies. The challenge that we see in the valley in many of these areas is capturing that salt. We have a diffuse source of salt that's building up over millions of acres of agricultural land in production and other areas. Capturing those salts and then concentrating them and then finding something to do with them, those are three major challenges and certainly ones that we haven't found the best solutions to yet. So,
Thank you very much. And now we're going to find out how to do it. Dr. Yu.
Thank you, Carl. All right. Good afternoon, everyone. It is really great pleasure to be on this conference. Thank you, Carl, for introducing, including me in the panel, and also thank you, Isaiah, for including NMSU in this project. So I'm going to talk about how do we do it, as Carl mentioned, and my colleague, Dr. Huiya Wang, is here. We have been working for 15 years on this project. So as we know that for brackish water desalination or municipal wastewater treatment, the water recovery is about 70 to 83%. That is mostly limited by the salts in that water, because calcium, magnesium, and silica, they can precipitate if the water gets more concentrated. So we need to add the acid, we need to add the anti-scalant to prevent the fouling and the scaling. Even like this, we still get about 17 to 30% of the water ended up in the concentrate. So David mentioned that surface water discharge, it may build the pipelines hundreds of miles to discharge into the ocean, or we can discharge it into the sewer, or the evaporation ponds like in New Mexico, or the deep well injection that Scott mentioned. But for all these concentrate management strategies, we are limited by the receiving capacity of the brine or the regulatory challenges and the environmental impacts. So we are thinking, can we achieve zero liquid discharge in a cost-effective approach? So then how we can achieve the brine valorization or higher water recovery, we come up with an innovative idea is here we talk about the brine. And the brine, this pilot testing is actually at the K. Bailey Hutchinson desalination plant that Scott mentions. In that desal plant, the original water recovery is about 83%. And the TDS is between 12,000 to 15,000 milligram per liter. It is saturated by silica. That's silica limited the water recovery. It also has high calcium, magnesium, sulfate concentrations. If we want to further improve the water recovery, especially if our goal is to achieve zero liquid discharge, we have to remove these constituents, the mineral scaling causing constituents from the water. So we did the... It's okay. Sorry, I did not look at this. Yeah, I do need to be careful. I think that...
Are you all right?
Yeah, I'm good.
You want to sit down?
No, I'm good. I'm good. Sorry. I do need to be careful. I did not know that there is. It's just for this small area. Okay, so we did the air stripping to remove the carbonate, and we needed the pH adjustment to 5. And then the new technology we use is selective electrodialysis. And the beauty of it is it can separate the monovalent ions from the divalent ions, because if we want to use this brine, the treated desalinated water for agricultural irrigation, and then we want the salinity is low, but also with higher calcium, magnesium, sulfate, the sodium concentration needs to be low. So that's how we use selective electrodialysis to get the dilute, that's the desalinated water for agricultural irrigation. And after that, we concentrate the brine to about 5%. It is mostly sodium chloride water. And then we want to use the bipolar electrodialysis. It is a new technology that can separate the sodium chloride into sodium hydroxide and hydrochloric acid. But it has a very high water quality requirements. That means we cannot have higher hardness, calcium, magnesium, and silica in it. Otherwise, it will scale the membranes. So after that, we use a chemical softening process to further remove the hardness and silica in that concentrate. And then the concentrate will be further concentrated through a brine concentrator. It is another new technology. It's recently developed by Veolia Water. We can concentrate the brine from 5% sodium chloride to about 10 to 18% of the sodium chloride. The reason is the higher sodium chloride concentration, we can get higher caustic soda and hydrochloric acid. Then in this process, we also have the desalinated water. We're going back to the selective ED to generate more water for agricultural irrigation. So for this technology, we demonstrated at the Kibele Hutchinson desalination plant, but everybody wants to know what will be the cost related to it. So we worked with Corollo engineers using the Blue Planet. We compare with a baseline. If you say this technology is good or bad, what do you compare with? So the baseline is we use the seawater RO to treat the brine from the Kibele, and also using the thermal concentrator and the crystallizer to get zero liquid discharge. And in this process, we can recover additional 96% of the water. It makes the entire water recovery for the brackish water desalination plant to about 99%. And the rest will be used, will be the salts for the landscape and landfill. So for this membrane-based ZLD process plus the brine valorization, and this is the process, and I just explained. This is the comparison of the different costs. On the far left is the baseline that the Kibele Hutchinson desalination plant uses. Pump the brine 22 miles for disposal. The cost is about 21 million gallons. $21 million. And then the blue bars represent the membrane ZLD process. And then you can see the cost is about $300 million for 1 mgd brine that we are going to treat. And it is even more expensive than the thermal ZLD process, because thermal ZLD process is a commercially available technology. And the membrane processes, even though they are commercializing, but the cost is still relatively higher. And if we consider that we can offset the cost with awarded brine disposal and water offset, means use the water for agricultural irrigation. For the thermal ZLD, it's produce the potable water, and the cost reduced is still kind of expensive. If we use the acid base generated for the on-site the brine treatment, because we need pH adjustment, the cost will reduce to about $244 million. If we can continue to convert all the brine into the acid and the base, you can see the cost is reduced to about $97 million, about 50% of the salt reduction. But the higher cost for the membrane-based ZLD process is related to the higher membrane costs, because these membranes are very new, and then they are not getting to the cost like reverse osmosis or the thermal desalination. And we are working with the national labs and with other projects funded by Norway. So we are testing all these new membranes. If the membranes could work, meet our target, and then the cost of this technology will be even lower than the salt disposal through the deep well injection. So that is very promising. In addition to the HCl and the NaOH, right now we're also working on recover all the minerals such as calcium carbonate, calcium hydroxide, magnesium hydroxide, and silica, because we can use all of these as the cement to make the cement. Sorry, I guess my time is done, but I just want to show you that the brine valorization is our future to address all the brine challenges. Thank you.
Thank you. Just one question. One comment is that we could give you a session just as long as this, not on the technical, but on the governance and the management of this. So it's a very complex issue, and maybe next time around we'll talk about some of the other parts of it. Yes, sir. Oh, laptop. Do we have time for any questions? Maybe one. Yeah, so do we have a question? You must, yes, sir.
What about the environmental impact of such a new technology? Have you,
Environmental impacts of such a new technology.
Oh, right.
And you have a microphone there.
I think there is huge environmental benefits related to these technologies because we can convert all the salts into all the valuable products, and then this will avoid the disposal of the brine and also avoid the disposal of solid salts if we do the thermal ZLD process. And then think about if we can reuse all these minerals on site, and this will also reduce the transportation. I think the benefits would be huge.